Yeah, good morning, students. In today's class, we just start with our what you can say the Miller indices. What we studied in our lower class, in the last previous class, we just studied about the Miller indices, right? In today's class, also we just deal with the Miller indices, right? So we already know that this thing, right? What is the solid and what are the different types of crystals, right? Now we'll just discuss in today's class the previous thing that we already known to us, that what is actually lattice plane, right? So lattice planes are nothing but when an imaginary points are joined, right? And in this particular manner, you can just see this figure. In this particular figure, it is very clear to you that the imaginary points they can be drawn in different ways, and these are nothing but we'll call this as set of planes, right? And why planes are necessary? Why? Because these lattice planes are nothing but they will give us the information regarding the maximum concentration of the atoms, right? So now, how this planes information can be mathematically known? So the scientist Miller uh, has given us the way to find out the Miller indices, and in this Miller indices will denotes the set of planes that is denoted by the integers, smallest possible integers. They are HKL planes. In the last class, we just discussed about this Miller indices. So we'll have a very brief again idea regarding how to evaluate this Miller indices. So before going to in depth about this Miller indices, first we need to I need to show you the how this planes is formed in three dimension, right? Particularly a cubic unit cell, right? So here we just I will let you know the how this can be, how these planes are formed. See, Miller planes. We said that this is called Miller planes. See, these are what thing you can just see this. This is actually the Miller planes, right? So before going in detail about this Miller indices, first of all, we will just have a very clear idea in detail information regarding the Miller planes, right? So atoms, we can just see this. These are imaginary points, and the imaginary points, whatever we are seeing, by means of which we can just draw different line segments, and these different line segments are nothing but we are calling it as the planes. And so you can just see that this is two-dimensional observation, a semantic figure of two dimension, where you can just see different values, right? So here you can just have any set of planes. Their orientation in the crystal is nothing but it is, we'll say that that is called HKL Miller indices. HKL corresponding to the number of segments in which the corresponding crystallographic axis. See, HKL planes means we deal with three dimension. So whenever we are going for three dimensional object, so we need to take three set of plane. So that set of planes are denoted by H, K, and L, which is resembling the three crystallographic axes, that is x-axis, y-axis, and z-axis. The intercepts of that x, y, and z, we just call that as A, B, C, right? And we say that that is actually the intersecting the or intercepting the planes. The value is given by A, comma B, comma C. This is a two-dimensional example which is given to you, right? It is shown in the figure. Right now, what is actually the crystallographic planes? So we want to actually examine. So what is the use of studying this crystallographic planes? As I told you, that the amount of atomic packing or the number of concentration of more concentration of atoms which are residing in the planes. So you can just we can have an example of iron foil which can be used as a catalyst. The atomic packing expose the planes, and these atomic packing is very important in knowing the concentration of the plane. You can just see this Miller planes, how this Miller planes look like. right? These are the imaginary points, and we can say that these lattice points, and this is in the shape of the cubic unit cell. And you can just see that at x-axis, y-axis, and z-axis, you can just see this particular thing is corresponding to. Let us consider the phase. If I extend this particular line, right? This is one phase. This is one phase, right? So now this is corresponding to x-axis, and this corresponding to y-axis, and this is also corresponding to the z-axis. You can just see that A, B, C are nothing but they are intercepting the planes, right? Now this is one plane. You can see this is one plane. You can see this is a completely one plane, right? And this is another plane. You can see I'm talking about B, right? This is another plane, and C, right? Exactly beyond this, this is the another plane, and this B plane is nothing but it is intercepting. B is the dimension, right? Which is intercepting the this particular plane, right? So like this, you can have a numerous example. So now this is one of the example how the x, y, z axes can be known in terms of the three dimensions A, B, C. You can just see how these planes are formed, right? So very clearly, see, this is what the plane is said to be. See the yellow mark, this is plane, and this is the another plane, right? And this the spheres, whatever you are seeing, that are the imaginary points, and we say that are lattice points, right? So you can just see they are parallel to each other. So A, B, C, they are exactly parallel to each other, right? So like this, you can have a different a set of planes in three dimension, right? See, this is the set of different set of crystal planes. So now I think that you got a clear idea what is actually the crystal planes. Now you can just see in the previous figure very clearly. This figure, if you see this figure, you can know that the distance between these two planes is same as the distance between this the another set of plane. So what is that distance d actually? How we can evaluate that distance d? So let us now, what we'll do is that we'll again go to our next PPT, in which you will understand how this is can be evaluated, right? Now, so now like this, having the two dimension. Just now we have seen the three-dimension picture of the mm, of the crystal planes, right? So just now we have seen this, right? You can see this is the crystal planes, right? So uh, now we'll just go to the further. See, considering the 2D lattices, two-dimension x-axis, y-axis, having the dimensions a and b. See, there are many ways of connecting this lattice point. See, this the distance is given by 1b, 2b, right? If you just choose an origin, right? So you can have the negative intercept also. See, so like this, you can just now we'll move to the Miller indices. So with respect to the crystal planes, mathematically Miller has given us the information regarding the reciprocal of these three uh, axial intercepts, or we say that these are the normal intercepts of a given plane, which has the same ratio as the reciprocal. And how to evaluate this? So first of all, we need to know the intercepts of the plane with the corresponding axes in terms of a, b, c, and take the reciprocals of the intercept. And as I already told you, the evaluation of the smallest possible intercept. So this is the different ways of drawing the lines, right? Crystal planes. Now this is can be extended. See, just now whatever we have done, this is for two dimension. Now we have just extended to the three dimension. So now you can see this type of figure. We need to calculate the crystal planes, and in the last class we just done that, right? So we have taken these two examples also. So you can have numerous number of examples. See, taking the intercepts, right? Taking the intercept, taking the reciprocals, and reducing it to a whole number. So you get different values. Now, see, this is what actually we are inferring here. Now we need to calculate. Just now I told you that we are actually this is the two dimension what you can say movement of the lattice planes, and we need to calculate what is actually this distance is all about. So now we are just representing this angle as 5, and the you can just see this is the origin what we have taken with respect to the x-axis. The intercept which is made on the x-axis is given by a by h, right? And the intersect which is made on the y-axis will be given by some a by k, right? So why I'm taking it as a only? Why? Because see the dimensions whatever we have taken in 2 dimension, that this is a and the x-axis, and also on the y-axis we have taken it as a. So the intercept will be varying, that is given by the intercept form a by h, and this is what a by k, and this angle is nothing but we are taking it as phi, and we need to determine this, right? So by seeing this, what we can do is that, see, by seeing the schematic figure, you can just see this is one value. See, this is a right angle triangle. You can see this is right angle triangle. This is another right angle triangle. You can see if you can imagine. So first of all, I will just take it with respect to the x-axis. So here sine phi is equal to the sine phi. When I take this angle is also sine phi. This angle is sine phi. So now I'm taking this right angle triangle. So sine phi is equal to opposite by hypotenuse, right? So what is that opposite side? The side which is opposite to the angle is considered to be the opposite side. So this is the opposite side. This is the angle. This is the opposite side. So we just taken that opposite side. The distance here. See, this is the angle phi, and this is considered to be the opposite side. So sine phi is equal to opposite by hypotenuse. Now this is the hypotenuse. This is given by a by h. So in a similar manner, when we go for the y-axis, you already know in the intermediate. So whenever we just go for the we can have an example in the kinematics also. The components of the velocity components in the x and y axis. The x-axis will the component will be reduced to the what you can say sine and cos. So in the same way, we are just taking it out sine phi, which is given by d by a by h, and cos phi d by b by k. So you already know sine square theta plus cos square theta is equal to 1. Here sine square phi cos square phi is equal to 1. This is for 2 dimension, right? So this is a d square. So just this is equal to 1. So sine phi value we already know. So we have just square it. See, we square this particular value component. So what will get d square by a by h whole square plus d square by b by k whole square is equal to 1. So now we just take d square common. So what you'll obtain this third value. This value will go to the numerator, and you will get h square by a square plus k square by b square is equal to 1. And we want this d value, right? This distance we actually calculating. So 1 by d square, this d square will go to the right hand side. So 1 by d square is equal to h square by a square plus k square by b square. Now this is the case for this plane we are talking about. So here for the 3 dimension value for the complete HKL plane. So here 1 by c. In the previous case, 1 by d square is equal to h square by a square plus k square by b square. So in 3 dimensionally, it can be written 1 by d square is equal to h square by a square plus k square by b square plus l square by c square. So if a, b, c, and HKL are known, then you can easily compute the value of d. Now this is the general expression actually. Again, we have to go for the reciprocal. We need to calculate, if you want to calculate this d, so this term will go up and this will go down, and you will get a square root of it. So we will get the value of exactly d, which is found to be 1 by root of h square by a square plus k square by a by h square and plus y square. Now that particular aspect is already mentioned right now. For 2 dimension, this is the case, and for 3 dimension, it look like in this particular format. So now we can just calculate the problem. We just go for any mathematical problem. So here, see, one example we have shown you. See, we calculate the separation of the, see, calculate the separation of the 1, 2, 3 plane and the 2, 4, 6 plane. There are two set of planes. One is 1, 2, 3, and that is represented by HKL. And this is what D part is HKL planes of which cell we are talking about, orthorhombic. So orthorhombic, Here A is not equal to B, not equal to C. So we'll just A with A is equal to value is given 0.82 nanometer and B is equal to 0.94 nanometer and C is equal to 0.75 nanometer. So what is the formula? 1 by D square is equal to H square by A square plus K square by C. Either way, see, if you want the D value, so in the numerator, this particular part will definitely change. So in general, we just write it down 1 by D square is equal to H square by A square plus K square by B square plus L square by C square. So we'll get 1 by D square is equal to, what is the value of A? You can just see that value of A is 0.82 whole square and the value of B is 0.94 whole square plus the value of C is C. We have taken this particular, we are talking about this 1, 2, 3. This is H, this is K, and this is L. So H is 1, K is 2, and 3 is 9 is here 3. So H square, 1 square, 2 square is 4 square. So we have written 2 square is 4. So we have written 4 here. 3 square is 9. So therefore it has written the value of L square is the 9. And the value of A, B, C is given as in the question. And whatever you get by using the scientific calculator, you can just evaluate this and the value you'll get D square value. See, 1 by D square, we want D actually. So just reciprocal of it. See, 1 by D square value, you got 22, right? So D square value, root of 1 by reciprocal of 1 by 22. So D is equal to root of 1 by 22 and you get the value of the interplanar spacing for the 1, 2, 3 plane is found to be 0.21 nanometer. So it is very easy to understand and easy to evaluate once if you have a concept. So definitely it will be easy for you to evaluate this. So in the second one, what is the B bit? So 246. So only the difference what you find that the numerator will change. Instead of 1, it will become 4. Instead of 4, it will become 16. And instead of 9 here, it will become 36. I will show you. See here, 4, 16, 36. And there the last denominator is same. See, denominator 0.82, 0.94, 0.75. Here also the denominator is 0.82, 0.94, 0.75. So what is the ultimate value? You'll get this ultimate value found to be 4 into 22 nanometer whole to the power of 4. And in this same way, D square is equal to 1 by 4 into 22, and you'll get the value of D as 0.10 nanometer. So you can just see that as the plane value, HKL value is less, so D is found to be 0.21, and the HKL value is increasing, so you see to 0.10. So they are inversely proportional. You can just see that this is the way how in the examination they will ask you such type of problem, so you can easily solve that particular problem. So with this, we can say that the interplanar spacing between the plane, either it may be 2-dimension or 3-dimension, you can easily evaluate by using the particular value what we have, particular schematic diagram. So in the case of 2-dimension and in the 3-dimension also, we can just replace that h square by a square plus k square by b square can be replaced with h square by a square plus k square by b square plus l square by c square. Now you can just see this this particular part. So in this particular value, see here again, I will go to the our previous one. So here you can just see that we have talking about the how to find the Miller indices, and there are important aspect of finding this Miller indices, right? So important features which are required to be discussed in the right. Next one is here. So you can just see this what actually we have done in the previous case. So the important features of Miller indices that if a plane is parallel to any of the coordinate axis, then you need to remember this important postulates of the Miller indices, which we have not discussed in the last class. See, what is a crystal planes, a crystal lattice, the interplanar spacing, how you can evaluate interplanar spacing mathematically, we just discussed, right? So one part of Miller indices was remaining. That particular part is what are the important things that things are important to remember while evaluating the Miller indices. So this is the important postulates by which you can evaluate the Miller indices, but you need to keep in mind this particular important point. So what is that particular point? So in the just now you have seen how the planes are formed and which are considered to be the planes, right? HKL. How one can designate the HKL plane with the schematic diagram. I've just now have shown you that how these planes, right, can be uh, schematically viewed. So if a plane is parallel to any of the coordinate axes, then the intercept will be taken as infinity. This is very, very important. If any plane is parallel to any coordinate axis, remember, if any plane is parallel to any of the coordinate axes, then the intercept will be definitely taken as infinity, and all the parallel equidistant planes have the same Miller indices. So if a plane is parallel to equidistant plane, right, all the parallel, if the planes are parallel to each other, so if they are parallel to each other, then they will have a symmetrical Miller indices or same Miller indices. The ratio will be same here. So the Miller indices define a set of equidistant parallel planes. Definitely, Miller indices means it actually the equidistant parallel planes. So if the Miller indices of the two planes have the same ratio, then the planes are parallel to each other. Which planes are considered to be parallel to each other? If the Miller indices of the two planes will have the same ratio, then that planes are said to be parallel to each other. Now, if HKL are the Miller indices of a plane, then the plane cuts the axis into H comma K and L of equal parts, right? So you can just see that when we are seeing that HKL, there is no comma. This is very, very important, right? If HKL are the Miller indices, when you designate the Miller indices, that HKL, right, that HKL is not denoted with commas, right? When you write the intercepts, then only we just write the commas. So if you forget to write the HKL instead of HKL, if you have written H comma K comma L, that is considered to be the points, and that is not considered to be the Miller indices. So this is the Miller indices of a particular plane, right? So see what is actually see in the previous case also, see for the cubic crystal, we just discussed that this is the case for the interplanar spacing for a cubic crystal for tetragonal, and just now we have taken general case of the orthorhombic, right? How the orthorhombic crystal system will have the intercept 1 by d square is equal to h square by a square plus k square by b square plus l square by c square. So in the notes also we'll have a very clear idea how to evaluate the interplanar spacing of the crystal system of either it may be cubic, tetragonal, or orthorhombic. So in general, we start with the orthorhombic and then we'll go for the tetragonal and the cubic. Why? Because when we just go from orthorhombic, here in the orthorhombic, the lattice parameters, that is A is not equal to B not equal to C. So in general, we just consider to be the orthorhombic interplanar spacing is considered the general formula to evaluate the interplanar spacing. As you move from orthorhombic tetragonal, so A is equal to B and B is not equal to C. So where you can just write instead of B, you can write A. So therefore we have taken the LCM, and it looks like that 1 by D square is equal to H square plus K square by A square plus L square by C square. Now as you move from tetragonal, see, and we are going in a reverse order. So why? Because of its general consideration. So here, when you go for the cubic crystal, so it comes to be 1 by d square is equal to h square plus k square plus l square. Here A is equal to B. What is the cubic crystal system lattice parameter? A is equal to B, B is equal to C, and alpha is equal to beta is equal to gamma is equal to 90 degrees. So in this particular section, you can just see that the interplanar spacing of all these three cubic crystal system will be differing from each other. So with this few important points of the interplanar spacing, right? So here you can just see, you can just by yourself, you can do some more problems by drawing, by seeing the Miller. See, whatever you are seeing uh, uh, on the screen, that are the cubic unit cell, you can just sketch the following directions of the Miller indices will be given to you, and you have to sketch it. You have to draw it in the cubic unit cell by showing the cubic unit cell and by shading that parts. So you can just trace out that thing and to evaluate the different values. So you can, within the cubic unit cell, so you can just go for so many problems, right? So now, you see, like this, he will in the examination, first he will ask you what are Miller indices and draw triple one and double one zero planes in a cubic lattice. And also he can ask you sketch the following planes of the cubic unit cell and 0, 0, 1 and comma 1 by 1, 2, 0 and so on and 2, 1, 1. So obtain the Miller indices. What the next one says that, see, this diagram is not possible now. So what you can do is that see, obtain the sixth question. What is given? Obtain the Miller indices of the plane which the intercept of a comma b by 2 and 3c a simple cubic unit cell, and draw a neat diagram showing this plane. Like this, he will ask you different questions, right? What you can do is that here we can just uh, calculate this value uh, of the Miller indices of the given plane, right? So we can, how we can just calculate it. See, first of all, you need to take this A. See, the first step, we'll just take it as 1, right? 1 comma. See, B by 2 is given. So what I have written? 1 by 2 with the C. See, I have taken the intercept. What is the, how to evaluate this Miller indices? First, take the uh, in coefficients of this intercept. So, what is the coefficient of A? 1. So, I have written here 1, comma. What is the coefficient of B by 2? So, I have taken it as 1 by 2, comma. So, I've just taken 3C is given. So, I've taken 3. So, then the next step that what you can do, you have to take it the reciprocal. So, 1 by 1, right? Understood, everybody? Comma. So 1 divided by 1 by 2. Can you see? Comma. 1 by 3. Can you see? So here, what it will be? Now it will be, right? Here, 1 by 1 is 1. Okay. Understood, everybody? And then it comes to be 2. So this 2 go to the numerator. So this will be 2. And lastly, you will get 1 by 3. I think that you are getting an idea. So here, so this is the, after taking the reciprocal, first of all, I have taken, in the first step, I have taken the intercepts. We want to evaluate the Miller indices of the given plane. So in the first case, I have taken 1 by coefficients. A coefficient is 1. B by 2 coefficient is 1 by 2 and 3C coefficient is 3. And then I have gone for the reciprocal and I got that 1 comma 2 comma 1 by 3. Now I have to take LCM. What is the LCM? 1 by 1, 2 by 1, 1 comma 3 is LCM. So 1 comma 3 LCM is what? 3. So I have to multiply 1 into 3. Whatever the LCM you will get, you have to multiply with each and every intercept, comma. So 2 into, see, 2 into 3, comma. So 1 by 3. You can just see 1 by 3 into, see, into what is LCM? 3. So now ultimately, what is the Miller indices you will get? Now we have just reduced that fraction into a whole number. So what I will get? I will get the Miller indices. So the Miller indices will always be represented with this 1 into 3 is, I have to write here 3. So remember, I am not writing commas. So 2 into 3 is 6. See, I have written 6. And this 3, denominator and numerator 3 will get cancelled. So what is remaining here? 1. So this is the Miller indices. So what is the Miller indices of the plane? A comma B by 2 and 3C. The Miller indices found to be 3, 6, and 1. So like this, in the examination, he will ask you different values of finding out how the Miller indices can be evaluated for different intercepts. So I think that you got a very clear idea about what we have done, right? So, right. So with this, I will just take leave for today's class. So in today's class, what were our objective? So our objective is that we want to actually know what is actually the crystal planes in the two classes. See, I'm going very slowly. Why? Because this is the conceptual classes. So if you understand this conceptual classes, then it will be easy for you to do the numericals. So then again, what I will do is that in the next class also, in the tomorrow's class, the next class, whenever the next class will be there. So in the next class, we'll just go for some more numericals, which is related to Miller indices and the interplanar spacing. Then we can go to the next one, that is Black's law. So before we're just taking a leave from you. So I think that whatever the things which has been taught to you has been very much understandable. And if you have any doubt, definitely in Tuesday's session, doubt session, whatever the doubts you are having, you can just will carry out the clarification part in the Tuesday's session. So with that, we'll take a leave for now. Thank you, everyone. Thank you for your patience.